Alright, now we'll get into chapter 9. Chapter 9 and 10, they are bonuses for you, yeah? Um, yes, for this dynamics, I'm just gonna go ahead and put that up for you. And again, I'm just a lot about reading, and we will go later on the calculations. So first, we have to know about the linear momentum, and some students have a background on physics. I think linear momentum, yeah, yes, from physics. So first thing you have to understand is, oh, what is moment? Yeah, momentum. Linear, of course, we have different momentums. So what quantity or quantities are a measure of how hard a moving or object is to stop. So something that is moving has a tendency to keep on moving. Yeah. So in order for the moving object to get to its stop, then you've got to play with some quantity or quantities to stop the moving object. So let's see what they are. So here I listed out for you is a mass inertia, your velocity, your stopping distance. It doesn't stop right away, by the way. You have a stopping distance. Eventually, yeah, it goes. Depends on how you stop it, by the way. And then, of course, the time it takes. Every time we have activity, we can measure the activity, yeah? And we call that time. And when we talk about the measurement of that activity, and we say like how long that is, yeah? And in fact, if you think about, we're measuring our let's just say age, right? 1 year old, 2 year old, 3 year old, 20, 30, 40, 50, 60, and you finish. So that depends on your calendar, and which is depending on your solar system movement, you know, orbiting around the sun, and also spinning on its own, the planet. And our planet is one of them in the solar system. So that makes the days and nights, because your sun go up and then your sun set, right? And then we divide that into 24, yes, units, which we call that a day, and of course a time. And 24 you get in hours, and we divide that into 60, 60 minute and seconds, so and so, yeah. So anyway, and that's how we're measuring time in this part of the universe. In terms of human knowledge, of course, we have no idea what the real universe knowledge is. And well, what are we, timing? We're timing about our own activity. Yes, your age always increases; it doesn't go down. Yeah, it's all just one-way train. And of course, you're actually measuring your biological system. Yes, and how it interacts with the environment. And we say like, oh, start the sunrise and then sunset, that's one day. 1 day, oh, 2 day, 3 day, and then we divide that to 7 days, and then go again, iteration, yes. Counting it again and again, the same thing, and then of course you add them up mathematically, and there you get your age. But the reality is, your activities of your system, yeah, against the environment. And of course, when you have interaction, every system that has interaction with the environment, they go old, yes, meaning like the system has start to create the weakness in the system by interacting with the forces, yeah, acting on it. So at one point, your system become weaker and weaker, because it cannot be able to have enough energy to withstand these environmental forces. So anyway, so right now, that moving object, yes, let's go back to this momentum, linear momentum. The same thing. You have an object, and that is in a motion, and you want to stop it. Okay, something that is going on, and you want to stop it, and you would take a look at the mass inertia, the mass of that, velocity, and stopping distance, and the stopping time. Okay. So momentum, we define it by force. Okay. So the force of movement, we call that momentum. Yeah. We have nothing but the force, the object. Yes, you have the force in something that is either moving or staying. Yeah. either moving or stay at a potential energy, where of course different setup. It's not just easy like a little ball like that. This can be many things. So, and the force of movement, the force of that movement when it moves, and we call that momentum. Yeah, so without motion there's no momentum, and the motion happened because of this force, and we take a look at the force of that movement and we call that the momentum. Yeah, so it is, again, since it is force, it is vector. The unit is a force, so therefore Newton, and then second, of course, because we take a look at against time. Yeah, and your momentum in this textbook they use G and equal to mv. Not very good, symbol to define, because people get confusion with the gravity. So anyways, m times velocity is called momentum. Okay, so mass, this is velocity. Mass is in kilogram, velocity is meter per second, kilogram meter is your force, so therefore you get Newton second. Okay, mass is kilogram, velocity is meter per second, kilogram, okay, meter per second is your momentum. Newton is the force, okay, is again mass and acceleration. Mass is kilogram, acceleration is meter per second square. And this is called Newton. Newton and second, yes. So if you multiply this with second, yes, another second, you will get this, which is momentum, okay? Because Newton is kilogram, meter per second square, times second. See? Will give you, this will cancel, one s is going to cancel, so you will get this, which is kilogram meter per second, because one of the s is canceled in here. Yeah, so you get kilogram meter per second is your momentum unit. Yeah, so therefore we can easily write Newton times second as unit of momentum. All right. Now here is the first example that you have to identify. Rank the following in order of largest to the smallest linear momentum. So we've got to rank it according to the linear momentum, and we know that linear momentum is, okay, g, and then you have your mass, and you're dealing with velocity. So before we rank, we have to get into it and take a look at it. Yeah, then we will calculate, of course, since momentum is a mass with velocity. So semi truck, your weight is 15,000, and here is your velocity. Yeah, that's 88 feet per second, 60 miles per hour. So when you multiply that, okay, you're gonna get 41,000 pounds second. Of course, change this into, that's the weight, okay, you have to change it into mass, okay, if you want to use this equation, and then times that will give you this. So you won't get it directly by multiplying, don't try to do that, because this one is in pound, which is a weight, okay, therefore you have to convert that into mass first. So convert that into mass, and then times the velocity is going to give you this. And we do the same thing, 32 caliber bullet. So bullet always have like a caliber, like 32 or 22 or 38 or, you know, blah blah blah. So this one is a 32 caliber bullet, and it goes with 1,000, feet per second, and it has like 60 grains, so that's a 0.00021 slug. So that's giving you mass directly. So therefore you multiply that, and you're going to get 0.21 pounds second. Of course, you have to convert it into pound, because we're doing a ranking. so we have to compare it. So even though you get the slug with the feet per second, you have to make sure that you convert the British into pound second, yeah, that unit into pound second to compare with this. Then we have 150-pound ski driver going with 183 feet per second. So therefore, again, we calculate the same thing, convert this into mass, and then multiply with this, change it into pound second, okay? Cheater, 120 pound, is going with 103 feet per second. We do the same thing. Get the mass, multiply with the velocity, convert it into pound second, and you're going to get 384. Yeah. In order to reduce time, I'm not going to calculate this for you. You can do this by yourself. Please just follow what I just told you what to do to convert this weight to mass. You will get that. That is your velocity. Pay attention to the unit. It's got to be the same system for you to be able to compare to rank it. Yeah. And then of course you will rank it in the way they want it: largest, next, and the smallest, by looking at these numbers, and you're going to go with this, followed by that, and this, and then that's the least. Okay, linear impulse. So the accumulated effect of forces acting over time is called impulse. So when a force is applied to a body, yeah, the body's momentum, meaning like because of that force, that body is in motion. And we're looking at this motion, yeah, force of that movement. So that momentum is going to change, yeah, when you apply it. Because you have no idea how this body, okay, how this body was moving before. It might be moving or might not be moving, but it does change, you know, the force of that the movement. So small force, large time. You have a large force is going to save more time, you know, because you have a large force that can go fast. Small force, of course, you're going to take some time to get that distance. Here is your impulse formula. We're going to integrate the force, yeah, with time. So what may be done to increase the linear impulse applied to a tennis ball by a tennis racket? So here's your tennis ball and here's your tennis racket. So you have to think about what may be done, what can you do to increase the linear impulse, okay, that you get by hitting this tennis ball with a tennis racket. So first, you're going to increase the force applied to the ball, and we call the accelerating the rocket, yeah, and racket, and then increase the time of force application, meaning you're going to loosen your strings if you want to increase the linear impulse, yeah. And don't forget, impulse is the accumulated effect of forces. Effect, don't forget this word. Not forces, but accumulated effect of forces acting over time, okay? So you have to look at the accumulated forces, okay, over time. Effects of forces over time. And first thing we do is increase the force applied to the ball, yeah. Second thing, we increase the time, yeah, time of force application to the ball. Now here is a particle, and that particle is acted upon by a time varying force, which is this guy. So now we start to put the function, yeah, force in terms of t. So rank the meaning like this time can be anything, and force is going to change according to whatever the time that you input in that function. So rank the following force profiles. We're going to rank it from greatest to the least. Applied linear impulse. And that linear impulse is because of the action of the force. And we have 4 situations going on, and we have to rank it. So first thing that you have to do is you have to come up with your impulse, how to calculate it. Yeah. So here we have a segment. So first, second, and the third segment for calculating impulse. So first you're going to go 0 all the way to 40, second 40 to 40 at 2, position 2 to 40 at position 3, and then we're going to go from here to here. You're given the force and time, and your impulses you're looking at the force and the time. Of course, we simplify it without going into calculus. Yeah, not doing integration, just go straight. So impulse of force and the time. And we have a force situation here. Yeah, I already told you. So how do we get it? All we do is we calculate by going, from 0 all the way. Okay. So you know that every time we graph like this, all you have to do is the force and the time. You calculate the area underneath of that graph in order for you to get the impulse. Yeah. So this is what we say is relation. Yeah. So impulse is directly proportional to the force, and impulse is directly proportional to the time. So, and of course, when you multiply, we will get a graph like this, and every time you want to find the resultant impulse, we get the area underneath of that. Okay, so even if you don't want to calculate it, all you have to do is just look at the area underneath of that, and you can be able to come up with at least, there has a greater area in A. Yes. When you go back here, you can be able to see which one is A. So this is A, B, C, and D. Okay, so this is A, B, C, and D. So this A, look at this area, yeah, and look at that area. That's a 20. See, and of course, look at this area, and then look at that area, yeah. So you can easily say this area is definitely more than that too. All right, and when you go back to the exam question, it's asking you rank the following force profile greatest to least applied near impulse. Okay, applied linear impulse. Sorry, linear impulse due to the action of that force. Okay, so you are going to get the area of this, and then that. So this is, when you look at it, it goes 1, 2, and then that's just 1 unit, and that's 1 unit, and then this is 40. Yeah, so you have like the rectangle and then 2 triangle. Yeah, triangle is a 90-degree triangle. So therefore, 1 by 2 base time the height. Your base is 2, yes, and then your height is going to be 40. Yeah. So I wrote the calculation for you, but this you could be able to do it in your head. So that's your first triangle. So that's 1 by 2. This is base is 2 and height is 40, and you have 2 of them, so I multiply by 2. So this and that will cancel, 2 and 2 cancel, so you have 80 here. And this rectangle is 40 here and 1 here. 2 to 3 is just 1 here, so that's 40. So that's altogether 80, 90, 100, 110, 20, 120. Okay, so that's how you calculate. So from here to here is 2.5. So you do the same thing. Triangle has a base 2.5 and then 40. Okay, so if you calculate it, and you have 2 triangles, so times 2. So this 2 will cancel out. So yes, so when you multiply that, you're going to get 100. Okay, because this is 2.5. Yeah, 2.5 times 40 will give you 100. The same thing here. So you have 20. This is a rectangle, so 20 times 5 is going to give you 100. And here you have the same thing, exact same thing, it's just inverted. So therefore D and F is the same but minus. It means that this is standing up and this is flipped down. So therefore I just put the negative right there for you. But for magnitude, we're dealing with the magnitude. It has nothing to do with the direction. So that's the same force. Like same impulse. So therefore you get AD and then BC. Okay. Newton's second law review forces, mass, time, acceleration, and we will put in the momentum, which is mv. Momentum is mass, time, velocity into this force equation. So acceleration is we're looking the velocity against time, mass still the same. So differentiation of velocity against time, and we're going to put that back into here, so we get dmv, okay, dt. That's just a way that we write in calculus. But it just says same thing, that we are studying the momentum, all right, against time is your force, because your impulse is force, yeah, and the time. The resultant of all forces acting on a particle equals the time rate of change of linear momentum. So we have momentum mv, and then of course your impulse, okay, we already studied I of t, I wrote it here for you, and your force, and we change that into using the momentum, and now we are going to use this in terms of g. Yeah, it's the same thing. Of course, now we put the g. And another way of writing, we have already learned that several times in previous chapters, and just put a little dot on it. That's just telling you that we're differentiating the momentum against time. Yeah, and you will get the force. Principle of linear impulse and momentum. So the impulse of all the resultant forces acting on a particle is equivalent to a particle's change in linear momentum. So we're going to put that into mathematical equation. Impulse, change in momentum, yeah? In calculus, we write it this way. It is we're integrating the sum of force, yeah? Differentiating with time. So you're going to get mv2 minus mv1. Now we're making a simplified version of it. So that's just telling you it is final, yeah, momentum minus initial momentum. It's going to give you how you go with the force, yes, from that time 1 to time 2. How do you prevent injury in the following situation? You have a ski diver landing, and you have a getting thrown into jujitsu, okay, jujitsu, sorry. So these are all like both activities using a lot of force in it, yes. So we can be able to, of course, use, you know, impulse, which is a change in momentum. If we play with that, we can be able to prevent injury of the ski diver landing, and also we can prevent injury getting thrown in jujitsu, okay. So here you're going to take all the initial momentum from the final momentum, and you're going to get the resultant momentum. Consider the two shopping carts shown here, and you have your cart B carries groceries and has twice the mass of cart A. Has nothing here and a lot of grocery in cart B. So neglecting friction, okay, right here we're going to neglect the friction if both carts are pushed with a 50-pound force, and we're going to push it with 50 pounds for about like 3 seconds, yeah. So now we have to calculate the momentum of that car and see which one is going to experience a larger change in momentum. So you have initial and final, yes, your mv1, and then your mv2, and then you're going to take it out, yeah. Of course, now you're given with the force, so I'm going to go back a couple of slides. I just want to come back here to show you how the force and the time is linked to initial and final, yeah, momentum. And we are going to apply this, yeah, and I came back from the previous slides and show you how we use this force and the time, yeah, 0 to 3 seconds, yes, 0 to 3 seconds. It's going to give you velocity 1 and 2 with the same mass, yeah. And what we're trying to find is if you have a larger change in momentum, which one? So they both are going to, be experiencing the same change in momentum, and that is because of this, okay. You're going 0 to 3 seconds with 50-pound force, okay, will give you the same, okay, change in momentum, because this whole thing is the change in momentum. Yeah, and that's what it's talking about, because momentum doesn't really care about anything but the force and the time, and you got both of them the same here in two situations. So therefore you're going to have they both, right, experience the same change in momentum. All right, nothing to calculate. Then of course we're going to neglect the friction at the wheel, and if both cars are pushed with 50-pound force for 3 seconds, now this time we're going to take a look at the change in kinetic energy. So your kinetic energy, KE, yeah, and you got to understand that this time, yeah, you are looking at like this, okay? Of course, you know that that is a momentum, yeah? If you take only MV out of it, that's a momentum. Now you can see everything very clearly. So kinetic energy going to use the force, you know, we have the same force. And of course, we also use distance, yeah, because your kinetic energy is linked to your work, yeah, which is your U. So work energy balance. So we have the work, yeah, component, which you use the force to go that meter, and then to go this 2 meter cart A and B. I read it wrong. So this is mass, okay? This is a 2 times of your mass. So this is weight heavier than that guy. So we're gonna have to go to a distance with this push on car A and B, which is lighter than car B. So here you have your force time, yes, distance is equal to your mass, okay, here. So you can see how this mass is going to change according to car A or B, which this guy has more, yeah. So therefore you can understand that your car A is going to experience a larger change in kinetic energy, yeah. Then that is because it's lighter, yeah. So it's lighter, so it will definitely go faster. This car is, and this one has a weight on it, so it won't experience larger change in kinetic energy than it was before. Meaning it will move, yeah, this one will move really good than that. Now you have 2 cases of the following situation, and you need to push a broken down car back to town. So first you push the car starting from rest with a constant force for about a minute, and you push the car already rolling at 3 miles per hour with a constant force for about a minute. So you have 2 cases, yeah. So in which case does the car experience a large change in momentum? So now we are thinking about, again, momentum, yeah, force and time, and a mass with velocity, moving with a velocity. Now we're given a velocity here, we're also given force and time here, yeah. So we are comparing that momentum in 2 situations and see which one is going to experience a larger one. So in both cases, assume that the ground level in friction is negligible. So first, you push the car starting from rest with a constant force for 1 minute. Second one, the car is already rolling at 3 miles per hour with a constant force F for 1 minute. You're going to push it, okay? So let's see this statement. So the first one is the car starting from rest experiences a larger change in momentum. That's not true, yeah? That's because the change in momentum, yeah, depends only on the force and the time. And you've got to really, really get it. It has nothing to do with the rest velocity, okay? Because if you remember, like we write it force, and I'm just going to make it easy for you. Force and time is the change, okay, in your momentum. which is your mass and the change in your velocity, because mass doesn't change. Yeah, instead of breaking m1v1 and then m2v2, I can also write this way. Yeah, because mass doesn't really change anyway because it's the same car. So the only that changes is your velocity, and that is going to give you the change in momentum. Yeah, and that depends on the force and time. It has nothing to do with initial velocity and a final velocity. Okay, so therefore you can relate that. So this is wrong statement. You will only look at the force time for momentum. You're going to look at the change in velocity for the momentum. So the car starting at 3 miles per hour experience a larger change in momentum. That is also wrong. Yeah, because if you really think about it, they're the same. Yeah, they both experience the same change in momentum, and it's because of this. Okay, and that's because the change in momentum depends on the force and the time. And when you look at the force, again, it's the same thing. Yeah, for two situations. Yes. All right. So if you are in a car accident from the perspective of impulse and momentum, are you better off being in a heavy or light car? Why? Is it better to have a car that is stiff or a car that will crumble on impact? Why? So let's see. So if you think about, I have to put this thing out here because there's no space. So a heavier car, if you think about it, it would have more inertial momentum. Since you have more initial momentum, you're going to have a higher impulse. Why? Because your impulse is completely related to the momentum, because your impulse is the change in momentum. Okay, which is, you can also write it this way: change in momentum. Yeah, and now you have a heavier, of course, car, so it will have like more initial momentum, so it's going to have a higher impulse, because the mass is going to be heavier, so therefore the impulse is going to be higher. So you're better off with a lighter car, that is less stiff, increasing the duration of the impact. So if you decrease the mass, of course you're going to get the weaker impulse. Okay, because as you know, the impulse is the effects of your forces. We're looking at them. Yeah, so therefore you have to find something that is going to have not a great deal of all right, mass, and also your initial momentum, and to prevent to getting you a higher impulse. And if you think about in terms of the duration, because your answer, you can also look at with this equation instead of that. You're gonna have this a change in momentum, which I write this way, but I'm just taking this mass out of the equation, so you get something like this, and you could write that. This is bracket. You could write that short and sweet this way. Okay, so it's the same thing, and that depends on your force and your time here. So so in terms of force, the duration of the impact, you're gonna choose a lighter car, and that is less stiff, because it's going to give you a how do I say, like a bigger, a longer time, a longer time to get to that impact. Okay, which can also relate to the impulse because of this connection. Okay, and it means that this can be connected to that through this. Okay, so I can write it here as impulse. So therefore you can also understand the situation of the lighter car, a stiff car is better, is because you can be able to increase that duration of impact, because it takes longer for the stiff car instead of the heavy with more initial momentum is going to crumple with that impact. All right, so suppose a billiard ball and a bowling ball This is a billiard ball, small one, and here is your bowling, yes, ball. They're rolling towards you. By the time each ball reaches you, they have the same linear momentum, okay? So your linear momentum, they have the same is set in this question. So you stop each ball from rolling by applying equal forces to each. So here is your force, you're gonna want to stop it, yeah? So assuming each ball may be treated as a particle, we always treat the ball as a particle anyway, and a friction is negligible, you know, the friction on that surface is going to be negligible. So which ball will take longer to stop? The surface where the balls are rolled, okay? So the ball would take longer to stop. So now you're also dealing with, you know, time. This one again for you, yes? Okay, and of course I am going to just write a delta V here. And we gotta try to find out which ball will take longer. So in order for this to longer, yeah, what is it that we can do to stop it? Is it the big ball or is it a small ball? Yeah, so that's what you're trying to find. Now we're gonna come back to what we have just studied. Yeah, I wrote it here for you when we go here. Yes, so this is the same equation here written systematically here for you. So here we're concentrating with the time. It doesn't really matter, yeah, because when you're forced to stop it, since they're rolling with the, you know, look at this, you know, velocity, yes. So when you think about the time to stop, you know, we have different masses, and we have your, of course, your initial velocity that they come at your hand here in this example, and then of course the force applied, yeah, to stop it. Since this is you, the same hand, so we could have just thought like you would apply about the same force, yeah. So your velocity, okay, initial velocity is the same for your both hands. Your force also got to be the same, yeah, because you are using the same hand pushing to stop that motion. So the bowling ball, the only thing, this two ball difference is the mass. So this guy is greater than that. So I would say, you know, like you should let me teach you something. Um, Calculate this way, okay, instead of using the calculus here. So we can do this like this, okay, and of course this is your force. Your force is your hand right here. It's the same thing, yeah. I'm trying to show you, and here is your mass, of course, and then your mass. This is smaller than that. Let's just give it like maybe 4 times or something. 1, 2, 3, 4 times is about, I thought, yeah, we can do 2, it's about 4. So this is gonna change, you know, since this has a mass 4 times, the duration, you know, is gonna take longer to stop. So it's I would say like the textbook answer kind of weird. I don't think this is correct. I would say like this is wrong. Yeah, I don't know why. Um, you have to go with bowling ball. Yes, because billiard ball is smaller than the bowling ball about 4 times. So unless this is correct, if the material, okay, material is making it, you know, like this and that about the same mass, then it could. But let me check if they state that or they don't. So suppose the ball and bowling ball are rolling towards you. By the time each ball reaches, they have the same linear momentum. Okay, so you stop each ball from rolling by applying equal forces to each, assuming each ball may be treated as a part. Okay, I got it. Okay, so here, yeah. So now they're gonna treat it as just a particle. This is a tricky question. Even I got into the wrong answer. So anyway, sorry. Since we're treating, okay, as a particle, treated as a particle, we're just gonna assume that they have the same mass. Okay, why? Because a particle would be zeisless, yeah. So anyway, so if we treat this as particle, then yeah, your both balls take the same, yeah, about take this the same about to stop, about of time to stop, yeah. So it's going to take about the same time to stop. So that's what I would say. This about is got to be here, yeah. Take about the same time to stop. So yes, even I got into, because I missed this, yeah. Okay, treat it as a particle, so you're gonna have both of them taking the same time to stop. If we don't have this, treat it as a particle, then you're gonna choose a bowling ball because it has more mass. Okay, so I just want you to, yeah, and be careful with this. Okay, it's kind of, for me, it's a little bit weird. You could go with either, I would say you can go with B or C, you know. Even though you treat as a particle, we still have to consider, like, this is kind of weird, the question. This is correct if we assume that the particle has the same mass. If we don't assume the particle has the same mass, then we could go with the bowling ball, yeah. And the next one is asking you, assuming that each ball may be treated as a particle again, so which ball will take a longer distance to stop. So here we go back to our calculation, you know, of our distance with time and the velocity equation. So here we're now looking at the distance. So here that's a change in time, your duration, divided by 2 times velocity, okay? Your initial velocity that these guys come in. So when we think about it, in order for us to get a longer distance, meaning like in order for this to go up, the time got to go up and the velocity got to go up, okay? So when you think about the billiard ball and the bowling ball, yes, this one is going to come in at a different velocity, yeah? And of course your velocity doesn't depend on the mass, it only depends on the distance, yeah, time t. So we know that we're treating them as particle, and we know that they have the same initial speed, okay, which is v1, and then of course they have the same force here, you know. I should write that down to stop them, yes. And of course, if we use this two equation to derive the final equation, so we can be able to see the distance, how to calculate it, okay? So if you have like again, this is pretty tricky, yeah, same as the last equation. If you consider the mass, all right, if you consider the mass, and we know that this mass is bigger than that, and even if we treat them as particle, yeah, you're going to think about the link to your kinetic energy, okay? So the same force here is going to take longer time and longer distance to stop if it has more kinetic energy, yeah, meaning like if it is rolling faster. So your bowling ball, because it has a bigger mass, right, going to travel the longer distance to get it stopped. So I would, you know, go with B, okay, again, in this question. This I feel like is wrong, because a billiard ball is it has a smaller mass. If we treat, okay, as a particle, and also at the same time consider the mass differences, okay? So yeah, this is going to take a longer distance, because it's going to definitely take longer time, yeah, this to stop because of its mass. If we don't consider the mass, they're going to take about the same time, so therefore they're going to reach to the same, yeah. So either this or this, it cannot be that, right? So this, I think there's a mistake in this question. if you want to verify with some number, we can create a velocity, as a 2 or something. Yeah, you can make it. And of course, you can also make the time, okay? Just give it some number and to put it in. So let's do like initial speed about 2 meter per second, and then your force about 10, okay? And then this 1 kilogram, and that's about 4 kilogram of 5, yeah? And then we can be able to put it into here, yeah? So change in time is going to give you instead of going, okay, this way, we can also, I'm going to give another equation, calculate here. So we can calculate it with 1 by 2 mv squared, and then use the force, okay? We can also calculate it this way by using that, okay, instead of the time, because we're concentrating in distance, so we can make a velocity, initial velocity, and then we're going to throw the mass and the same force is set it so, yeah? So if you calculate it, it's going to come out your bowling ball has like about 1 meter, and your billiard is going to go about 0.2 meter. I don't know if you can see it or not. I can write that down for you. So for billiard ball, okay, which is the red one here, 1 by 2, okay, your mass, I'm going to just make it 1. And if you go with the velocity 2 meter per second with 10 Newton force, okay, like that, you will get about 0.2, okay, distance. Now the other one, we can calculate it by making it the same equation, 1 by 2, and let's say the 4, okay, 4 times greater than the ball, billiard ball, and then of course the velocity, the whole square, is 2 square, and then divided by time, sorry, not time, force, okay, the same force, okay, you're gonna get, I can make it 5, yeah, to make it easier to calculate. Let's say like the bowling ball is 5 times more than this, so let's say this is 5, okay, and this is 1. So if you calculate with 5, you're gonna get about, I'm just trying to make it easier for me to calculate in mind. So this, you'll get about 1 meter, yeah, for the blue bowling ball, and this one 0.2 meter for the billiard ball to come to stop, yeah? So you can also check it that way. So I would just say either this, and if we force, the mass are the same for the particle, because it doesn't say, it's tricky question, you can also choose C, but not A, okay? All right, I correct that problem for you, and then we're going to get into particle impulse and momentum, linear impulse momentum principle. We'll get into it, and we're repeating the same thing. This is your momentum, we calculate mass, time, velocity, and then your force here, and A, and then we're gonna do derivative right here for you, yes, differentiation, so mv, and then of course we can write it this way. So that's just a review from what we have already studied. So the resultant of all forces, the thing you need to understand is only this sum, yeah, acting on a particle equals the time rate of change of linear momentum, which is this guy, yeah, it's just a calculated area. We're just saying like you can be able to calculate by using the time rate of change of momentum, timing this guy, and here this is the rate of change, okay. Principle of linear impulse and momentum. So you have the impulse of all the resultant forces acting on a particle is equivalent to the particle's change in linear momentum, the same thing, yeah. We're stressing on the sum of the, all of that, mean like the impulse of all the resultant forces, we can be able to calculate it in this way. So all the resultant forces acting on a particle is equivalent to a particle's change in linear momentum, okay, which is the same thing that we've been talking again and again. So how do you prevent injury in the following situation? I feel like we're I feel like this is the same slide so we've been doing, so it looks like repeated in here. So let me check going down why. Yeah, this is the same thing. I don't know why this is repeated here. Ooh. Okay, anyway, so we can just erase that. It looks like there's some problem in there. So let me try to remember which slide I should get rid of. Yeah, it is repeated. So I am going to we have to stop it actually right here. Yes. Anyway, so we finish here, and I think there's some confusion in their slide. So we'll jump to actually here. So if you are in a head-on car crash with a stationary wall, so you have a wall and then you're gonna have your car crash, head-on to the stationary wall, meaning like the wall is just a standalone. So from the perspective of impulse and momentum, are you better off being in a heavy or light car? So is it better to have a car that is stiff or a car that will crumple on impact? I think I already did this problem as well. Okay, so now we come into linear impulse momentum. It looks like the slides were repeated, so I'm going to go ahead and get rid of it for you, okay? So now a linear impulse momentum for a system of particles. So we will write down all the equations that we have already studied. So that's your linear impulse, momentum, and then the system of particles. System of particles, we just add them up, and I refer to the number of particles in the system. The rest of them are the same thing. The only thing that is different is we use I to represent the system of particles. Conservation of linear momentum. So if the resultant force on a system of particle is zero, during an interval of time, your linear momentum got to remain constant. And we can put it into the mathematical equation like this. So here is the sum of your system of particle, and we're calculating the final momentum, and this is your initial momentum of the systems of particle. Yes. And here, of course, this is the change, and it's equal to zero. And this is just showing you, if the resultant force is zero, you're gonna have this linear momentum is going to be constant. So what you can do is you can be able to say that initial momentum and the final momentum, okay, but by moving this component to that side, they are the same. So you will get something like this, okay, vi, and then final is equal to the initial, like that, okay. Initial 1 and final is 2. Then we come into the problem. So you are an astronaut, you're floating in the vacuum, or outer space, and you have been stranded a distance away from your spacecraft. So which of the following options would you choose to help propel yourself back to the craft? This is a very fun question for you to understand how the space material works. Okay, it's just a space in the outside, right? Outer space is a little bit different from the Earth atmosphere and the gravity. So this example is just a very classic application that we use in conservation of momentum, of course, in the outer space, because in outer space we have no air, no friction, and then we don't have external forces, so they behave a little bit differently. So as you know, the linear momentum is conserved. Of course, this is a completely isolated system, so you have what I have just showed you about this, okay, conserved, meaning like it's completely zero, and you have the initial momentum and the final momentum, they are equal. So when you throw when you wave your arms and kick your legs, yeah, that just moves part of your own body around, but no external forces apply. So your center of mass is gonna stay exactly the same way. The second one, so that's wrong. Throw a wrench toward the spacecraft. So that is going to move the wrench. Yeah. So here is a spacecraft, and then you're going to throw the wrench. Okay. So this is you, and then you're going to throw the wrench towards the spacecraft, like this. Okay. Um, so that moves the wrench towards the spacecraft, which will cause you to move even farther away from the spacecraft. Okay, and that's a really weird thing that you need to understand, because you're throwing the wrench toward the spacecraft, and that is going to move the wrench towards the spacecraft, and which is going to cause you to move farther away from the spacecraft, okay, because you're tied like that to it. Now you're going to throw a wrench in the opposite direction of the space, okay, and that is correct, is because if you do like that, by conservation of momentum, you're gonna move in the opposite direction of the wrench, okay, which means toward the spacecraft. Wrench will go opposite, and you will go to the spacecraft. Okay. It might be a little bit difficult for you to be able to understand the nature of space, where there's no friction and no external force, and no air. It's definitely behave a little bit differently. So if you want to move towards that, and you've got to give in this case, wrench is kind of like the force that you're using in the opposite direction of it. Okay, so you will go towards the spacecraft because you are throwing the force into the opposite direction of it. And none of the above is completely wrong, because one of them is correct. Yeah. So that's exactly the same as how your space rocket works. So when you study the rockets, in order for it to go forward, you have to have your exhaust gases backwards, going that way. And so it's going to move this body, or the rocket body, forward. Yeah. So you're pushing exhaust gases exact same 180-degree opposite direction. So that's how you move. By throwing the wrench to the backwards position, you will move towards the space craft like that. Okay, all right. We will go into another example. You only have to listen to them. Yeah. So we have 0.1 pound bullet, and that is traveling at 1,000 feet per second when it strikes a 5 pound, okay, which is this guy right here, traveling at 10 feet per second on a smooth surface. Now you have this bullet hits the block, okay, centrally, and is embedded in the block, okay, which, look at, this guy is going to come into here and hit it here centrally. And which of the shown path do you think most closely approximates the direction taken by the block following the impact? So here's your impact, and this guy is going there. The bullet come in here and hit you at the center, and we gotta figure out where is it going to go, okay, because of the effect of that force. This one, I would just tell you that you'll have to calculate a little bit, and some tangent is involved in it, because you can't be able to calculate it by just doing conceptually, okay? You need to use these values to be able to calculate, and of course you don't have to calculate in this course, so I'm just going to go ahead and calculate and tell you, like what they are. Of course, this and that is automatically eliminated because it can never go, these direction because of the way the force come in, and then you going that way. So you have a two major force going that direction and then this direction. So therefore these two direction will be eliminated immediately. So you're left with this, and that. Okay, so now you're hitting with look at this. This is a very, very big force. Okay, and you're just going with a 5 pound with a 10, all right, feet per second. So when you think about it, okay, you can be able to calculate, okay, the momentum going this way and the momentum going that way by using, MV, yes, and of course your initial and then your final, so go initial, final, and then you equate it, and you're going to be able to get, okay, be able to get this velocity, and which is going to be the final velocity component. So you can be able to get it, and of course your bullet velocity is going to be higher than your this object velocity, okay, the object that got hit. So if you want to think about the direction, you can eliminate B, okay, directly. Because it can never go to that direction because the force, the I would say like the velocity that's coming here is way, way higher than that. So now you come down to C and D. C cannot happen because that is to see like how perfectly 45-degree angle that it is going. So we can also eliminate that. So therefore you can get D. And if you calculate it, you will also get the same thing for this D, okay, because of this angle. I'm just trying to teach you how to visually calculate without actually going into the calculation. But if you actually go into the calculation, you're going to see this angle is lower than that, horizontally. So this is my reference datum, the one that I use as a reference to calculate this angle. So this angle is higher than that, so therefore this path cannot happen after the impact, because this guy with a way, way higher velocity than this is going to push that over. So therefore we have D for answer. Because if you calculate, that's only 10 feet per second. And look at how small this is, and you have like a 5 pound, that's like a 0.1 pound, so therefore it would definitely push you to this direction, D direction. Alright, now the next one is consider that two bullets of equal mass have been fired with equal velocity toward a wooden block resting on a frictionless surface. So one bullet is rubber and bounces off of the block. So while the second bullet is made of steel and embeds in the block upon impact. So in which case does the block have the larger velocity following the impact? So let's take a look at that. Of course, you can always draw. Yes, you have a two bullet and they have an equal mass. So you can do this thing in your head like this, and then it's been fired, with a velocity, and you have a velocity, fire with a velocity, and then of course it's going to hit right there. We don't know if they're equal or not, so let's take a look at it. So one bullet is rubber, so the very first one is rubber, but even if they have a different material, they have equal mass. Don't forget that. And the other one is made of steel, okay, and embeds in the block upon impact, meaning like it's going to go straight in, okay. So in which case does the block have the larger velocity following the impact? So we have to try to find the final velocity, if they have a larger velocity or not. Is that the rubber bullet or steel bullet, or would they have the same velocity? That is, we will consider the material. So you're dealing with the rubber and the steel, but they both have the equal mass. So when we think about the rubber, we understand the nature of rubber is elastic. Yeah, and the other one, of course, your steel is inelastic. So therefore, when it hits, okay, its velocity is going to be smaller than the rubber, because your rubber is definitely going to have a greater velocity. Yeah, in the rubber bullet case, because um, because of the elasticity, yeah, because this elastic collision of that rubber ball with that wall is going to transfer more momentum to the block than an inelastic one. Yeah, again, when we say momentum, don't think like something that go into the wall. You know, we're talking about transfer the greater momentum, meaning the mass of that guy, which is the same, but then now we're, since the mass is the same, we're looking at only the final velocity. Yeah, so final velocity, when you think about it, since the steel has a heavy, you know, material, so it will definitely reduce the final velocity, and rubber has a elastic bouncing material, so the final velocity is going to be greater. So therefore, since the final velocity is greater with the same mass, you're going to get the, you know, larger velocity following the impact, which is this guy right there. So again, this book is a completely conceptual dynamic, so therefore it emphasize in reasoning, okay, instead of tedious calculation. So here, if you want to take a look at how we do it mathematically, you have your steel and you have your steel bullet. Mass is the same, so we write it there, and velocity, initial velocity, is the same. We have to come up with a final velocity. So when you come up with the final velocity, yeah, you're going to get the bullet and calculate it this way. They will stock together like that because of the steel will go straight in. For rubber is elastic, is elastic. The way that we write the momentum for the getting the velocity, final velocity, yeah, you will write down uh, rubber bullet mass, and then initial velocity, and then your bullet, okay, final velocity, because it will bounce back. So you have this, okay, bullet velocity coming out, and divided by the moment of the block. Okay, this is just a impact to it, and you will be able to get the velocity of the block. Okay, it's a little bit different from this one is where the steel bullet and the block are together. This one is the block has the block, and the rubber bullet has the rubber bullet velocity. Yeah, distinct velocity, because of the material that made this bullet is rubber. Yeah. So it means that the block will have its own velocity, and the rubber bullet will have its own final velocity. Okay, so this is block, and then this is rubber bullet velocity. So that's what you see. Okay, this one is a steel bullet. Okay, is inside and with the block together. Alright, then we go into the example problem. Impact. So impact is the only thing that I asked out of the lab for the impact velocity, and even though I didn't really stress on it, if you don't want to do it, it's okay. So anyway, so impact, so when two bodies collide over a very small interval of time and exert a relatively large forces on one another, you're going to get the impact. So you have two bodies and they collide, and of course that collision happened in a very small amount of time, and it's gonna, this collision is going to exert a relatively large force on one another, so it get bang. So this ball is going to hit that ball, and that ball is going to hit this one, and then that one, depends on how it will roll, okay? Because they're all near, positioned. So let's take a look at it. So the line of impact is very important, because every time you have an impact, you have to calculate where the path is. So the line drawn between the centers of the mass of the two bodies that is colliding and pass through that contact point, we call that the line of impact. Okay, so it's this guy. So plane of contact, this is line of impact, and this ball is going to come with that velocity, and this ball, okay, and ball A and ball B, they hit, and then it's going to go back out with a different velocity, okay, and the ball A is going to go with, after the impact, go out with that velocity. This is final, and that's a final momentum. This is initial, okay, and then of course this is initial. So this two coming in from the opposite direction hit, the ball B will go that way, and the ball A will go that way with new, okay, velocities. Plane of contact, here's a plane, line of contact, and here's a plane of contact. So the plane of contact is, they're perpendicular, yeah, to the line of impact, and resize at the contact between the two bodies. It's a little bit different. Line of contact, say this one is that line drawn between the center, yeah, center of mass of the two bodies, and then it's going to pass through that, you know, point of contact, which is this guy right there. I forgot to show you, yeah. And plane of contact is that goes perpendicular to that line of contact, okay, between the two bodies. So coefficient of restitution is important. So energy is generally not conserved during the impact because a lot of the rigid bodies are inelastic. So energy is lost due to your plastic material deformation or your heat or the sound. We can't get it back. Yeah, those kind of energy, we lost them. So if the bodies stick together after the impact, it is perfectly inelastic. Okay, we lost all of that. And if energy is conserved, the impact is perfectly. If the energy is conserved, the impact is perfectly elastic. Yeah? So if we wanted to save the energy, we know that your collision is elastic. They don't stick together. So a measure of the elasticity of the collision, and we call that coefficient of restitution. Okay, and of course we use a little e, and 0 mean they're perfectly elastic, and 1 mean perfectly inelastic or plastic. Yeah, it's just E and P. So E is elastic, coefficient restitution is 0. P is plastic, which is inelastic, is coefficient of restitution is 1. Okay, don't get it reversed. I don't know why a lot of the students get these two values reversed. Okay, you give me like coefficient of restitution for elastic is 1, and then coefficient of restitution for inelastic is 0, and I don't know how you do that. It's the opposite. Yeah. Now name the examples of impacts that are nearly perfectly elastic and perfectly inelastic. So let's take a look at this. So elastic is your super ball, and your plastic is your, this is just a weird example, wet toilet paper is going to be plastic. Meaning like there's no elasticity in it. Coefficient of restitution, so the ratio between the restorative impulse and the deformation impulse. Okay, when you calculate the ratio of that, you can be able to calculate this E number. 0 for elastic and 1 for inelastic, and we get that value from this operation, which is division. So all we do is restorative impulse and take a integration, yes, and divide it by the deformation impulse and take that integration and divide it, yes, and you will get the E. You don't have to worry about this either. Nobody is going to ask you, but you definitely need to know elastic is 0 and inelastic is 1. Okay, at least that you need to know that this is plastic and this is, I would say, elastic. Alright, and here it's just showing you, you have your momentum, and here momentum, and you collide, and then you're going to go off with the final momentum. Yes, this is after the impact, and this is coming into the impact. And of course we will show this D and R, integration like this, for us to be able to get this value. And that's just showing you how they come in and then how they go off. and pay attention to the direction. Yeah, when they come in, see, it's like that. And then when they go off, and then you're going to get your restorative impulse. That is deformation because they collide. Restorative after the collision. Coefficient of restitution, it relates the incoming, again, here is incoming and the outgoing particles with these two particles here, velocities along the line of impact. Okay, what it meant here is that we can also relate this value, yeah, to the velocities. So here you have a line of impact velocity. Prime means that is after the impact, and this is before the impact. Okay, some students use it like initial and the final. That's okay too. Yeah, and this is how you simply calculate the coefficient of restitution by using the final and the initial velocities. Okay, all right. So direct central impact. So direct central impact is when you look at it, the incoming velocity and the mass A and B, and here's your line of impact, and they collide, and then they go back out with the final velocity. Okay, and this is called the direct central impact because it just come in, yeah, 180 degree, and then of course they are 90 degree to each other, and then bang, and then go back straight out in the exact path they came in. Okay, like that, and thus we call it direct central impact. Oblique central impact looks like this. They come in this way but go off that way. Then we have impact type. So name examples of direct and oblique central impacts. Yeah, you have direct and then you have oblique central impacts. I already showed you how they come in and go by that way. Yes, and then they come in and then of course they go by this way, and that's your oblique. Yeah. All right, I'm going to stop the first video here by giving you the name of the examples. So the direct is your head-on car crash. Your oblique is your billiards, yeah, when you play the pool.